Well, hello ladies and gentlemen, and welcome to our last bit of review before the final exam here, and of course your AP exam on the 14th. Now, I just want to go through a few basic ideas to help look at some of the math and other concepts we've discussed through the year. And the first thing I'd like to do is take a look at creating solutions of different molarities or different concentrations. If you're asked to create a solution of a certain molarity, the easiest thing to do is find the molar mass of the molecule. So if we take glucose here, you find the mass of individual carbons, hydrogens, and oxygens and multiply them by the number of atoms for each of those particular elements. Combine them, and that will give you the mass for 1 mole of that particular molecule. So in this instance, it's 180 milligrams per mole. So if you need a 1 molar solution, you put 180 milligrams of the solute in the beaker and then fill it up to 1 liter. So if you know you need a liter of a half concentration or 0.5 molar solution, you just cut that in half. All right, let's see. The pH scale. The biggest thing to remember with the pH scale, the most frequently asked type of question, is the difference in concentration of hydrogen ions. Again, it looks at the dissociation of water. So you've got the hydrogen ions and the hydroxide ions, and pH is just a measure of the concentration of those hydrogen ions. Now 7 is always the magic number. Here we have equal number of hydrogen and hydroxide ions, so it's neutral in its hydrogen ion balance. Now, as the pH gets progressively further from 7, the acids and bases become exceptionally strong. Here down at a pH of 1 or 0, you have very strong acid, and then at 13 or 14 you have very strong bases. And what you'll often be asked is the strength of or the change in hydrogen ion concentration as you move steps along the scale. Every step is a power of 10. So to go from a pH of 6 to a pH of 4 is 10 times 10. It's 100 times stronger to have a pH of 4 than a pH of 6. The other thing you occasionally may be shown is the actual hydrogen ion concentration. Here with a pH of 4, the exponent would be a negative 4, it would be 10 to the negative 4 molar. Now everything has to add up to 14, so if they give you the hydrogen ion concentration being 10 to the negative 4th, then the hydroxide ion concentration needs to be 10 to the negative 10th. Functional groups. These are easy points, easy points. There are almost always questions asked related to the functional groups, and I recommend reviewing these charts, or this chart particularly, because it's well organized. But you can also look in your textbook, pages 64 and 65. Now, things to remember. Let's see, the hydroxyl groups, the OHs, they're also often found in alcohols. So if it ends in OL, you'll know it'll be an alcohol, and it's often a result of fermentation of carbohydrates. You think of like ethanol, it could be made from potatoes, corn, whatever the case may be. So if you take these starchy foods, these carb foods, you can ferment alcohols. So hydroxyl, think alcohol and carbs. Carbonyl group, think the glycerol and the glycerol and fatty acids. You have the carbonyl group with the carbon double bonded to an oxygen. Again, the glycerol and fatty acids. Okay, carboxyl and amino. If you remember the structure of an amino acid, you have the central carbon. Let's see, you'll have your carboxyl group. So you have a carbon double bonded to an oxygen, and that carbon's also bonded to a hydroxide. And then you'll have your amino group. You'll have hydrogen here, and then you have your side chain. And remember, it's these side chains, the R groups, that can differ and give amino acids different properties. Now, sometimes you'll be shown just this structural formula here. If you see nitrogen, you know it's a protein. Okay, nitrogen is a big giveaway for proteins. Nitrogen is also found in the nitrogenous bases, obviously, but if you see this particular structure where you have a carboxyl group on one end and an amino group on the other end, you know it's an amino acid. And then again, pay attention to the R groups because they'll give the amino acids their different properties, primarily being hydrophilic or hydrophobic. All right, let's see. Phosphate groups. Phosphate groups, where have we seen phosphate groups? Well, in the sugar phosphate backbone of DNA and in the third phosphate, or first, second, and third phosphate groups of an ATP molecule. One thing to note here, some of the oxygens are negative, so that helps explain why DNA is a negative molecule. So again, just review these really quickly, be able to identify some ideas related to them. Let's see. Remember, enzymes, which are a class of proteins, end in ase. Carbs will end in ose or -ol for alcohols. Methyl groups. Methyl, just a simple little carbon here. Remember, we talk about methylating DNA. The DNA coils up, and basically it's inaccessible for transcription. So methylating DNA, adding these methyl groups, can in essence switch off genes. Disulfide bridges, easy to spot when you see the sulfur there. You remember that proteins have a particular three-dimensional shape, and part of that shape is stabilized by these disulfide bridges formed by the sulfhydryl groups. Eggs are stinky because as the proteins in the eggs decompose, you break these disulfide bridges and that releases the sulfur. So again, if you see sulfur, it's a sulfhydryl group, and think proteins. All right, again, 5-10 minutes reviewing that stuff and that'll help. All right, the Gibbs free energy equation. Don't worry about memorizing the equation, just understand the relationships. That's the key here. Free energy is energy that we can use to do something, okay? Energy available to do work. Well, how much energy we have to do something is going to depend on the total energy we have in the system, which is termed enthalpy. So it's all the energy that we have in a particular system, minus, and that's the key here, minus the disorder. This is the disorganized energy. So we know that entropy is a measure of disorder, and if you think of it, the greater the disorder, well, the less energy is available to do actual work. Okay, so again, the take-home, don't worry as much about the equation. Just recognize the energy you have available to do work depends on how much energy is in the system and how much disorder there is. And the more disorder, the less energy is available to do work. All right, enzymes. Know your enzymes. Enzymes are quite helpful for the exam. The primary function of enzymes is to speed up chemical reactions. Okay, so they act as these biological catalysts by speeding up reactions. How do they speed up reactions? A couple different ways. First is they lower activation energy. So think of activating a cell phone. You know, the activation energy is the energy needed to start the chemical reaction. Now notice you don't get any more energy out of the reactions. It's just that it happens at a lower energy, and I don't like this curve particularly. It should back up here a little bit. It happens earlier, okay? So it lowers activation energy and speeds up the reaction rate. Now, how does it do that? Well, first of all, it will stress the bonds of the substrate. Remember, the substrate is the molecules that attach to the active site of the particular enzymes, and what the enzyme can do is stress the bond. So if we imagine this being, two atoms held by a chemical bond, it will stress that bond. And if you stress bonds, it's easier to break them. So it happens faster and at lower energies, or at lower activation energy. Now, enzymes do have this sort of induced fit model that people have embraced. And the idea is the substrate will alter the shape of the enzyme in order to allow the two molecules, in this instance, to juxtapose themselves in such a way to form a chemical bond. And what's important to note is after the product is released, the enzyme goes back to its original conformation, its original shape, so that it can be recycled back and perform that reaction again. How fast? Up to maybe 400,000 times per second. So pretty remarkable. So enzymes are important because they allow reactions to happen at speeds needed for life and at temperatures low enough to not compromise protein integrity. And not like its honesty, but it's like its shape. Okay? In this next section here, we will go over photosynthesis and respiration. to look at a very important section for the AP exam.